very happy to be given the opportunity to introduce the first speaker, and who's going to talk on one of the topics of one of the Clay Millennium Prize projects. Peter Constantin was educated at the University in Bucharest and did his PhD under Shmuel Agmon at the Hebrew University in Jerusalem. After a long and distinguished career at the University of Chicago, he moved last year to Princeton, where he is the William R. Keenan Jr. Professor in the Mathematics Department and Director of the Program of Applied and Computational Mathematics. Over these many years, Peter, through his work on numerous aspects of the rigorous treatment of fluid mechanics and in particular turbulence, has been inspiration. And it's a great pleasure to introduce him and ask him to give his talk on the Navier Stokes equations.
Thank you very much. I hope you can hear me. I'd like to see the board. It's a great honor for me to be invited to speak here, in particular in view of the great occasion we're celebrating the opening of the Math Institute, and I think that I'm both very pleased because I see with this occasion we have, and I would like to thank the Clay Foundation for facilitating this. We had a wonderful workshop on problems related to the Navier Stokes and fluids, and I think that in some sense that justifies all this endeavor. We are here to do math, and that's what this building is about. So I will talk about Navier Stokes equations, and I'm imagining an audience of mathematicians, but not necessarily, although I see some of my friends here, I'm imagining that some of you might have wished to forget some of the analysis. So I will try to remind you some of the basics. I have a little bit of trepidation about the introduction. I was, because you mentioned the fact that this will be accessible to all. I'm hoping it will be accessible to all mathematicians.
That's what I meant, yes.
So here is the problem. Let me put it up a little bit, and then I'm going to explain each term. Okay? So these are the Navier Stokes equations. I also would like to refer also to my colleagues, the people who are actually experts, came to the workshop and so forth. With a little patience, at the end, I will give them something. This is, after all, the name of this meeting is a research conference. So at the end, I will give them something that is new, fresh. By new, I mean order of months, and I put it in the archive maybe 2 weeks ago. So the problem, let's see. U is a velocity, and it is a function with values in R3, so it has 3 components. It depends on 4 variables, x in R3, and time. Time is non-negative because of the way things are. You'll see in a second. This equation is the momentum balance, it's Newton's law. And here the first term is the time derivative of u, which is the acceleration at a fixed point x. This term is a first order derivative, so this little triangle is a derivative in each direction. So you have 3 directions, and this dot product means u1 dot d dx1, u2 dot d dx2, and u3 dot d dx3. So it is a vector field differentiating u itself. So this is if you want, these are 3 equations written here. Okay. Nu, and you'll need to remember that, nu is a number, and it is the kinematic viscosity, positive or 0 number. It has units of, let's say, length square over time, so centimeters square per second if you want. A normal temperature in this room, maybe about 10 to minus 2. This is the Laplacian, Cartesian Laplacian, two derivatives in each direction, a trace of the Hessian. So you have a second order differential operator in x. This is derivative in time. This here is the gradient of pressure. It is a physical pressure, but it's not the hydraulic pressure that you can imagine that you learned in high school from Torricelli and things like that. It is a force, because after all this is Newton's law, acceleration equals force. Mass is 1 here. The density is taken to be 1, so everything is normalized there. So this is an internal force, a force that keeps the fluid from breaking apart and maintains this other constraint here, which is the divergence of the vector field being 0. Divergence means the one directional derivative in direction 1 of component 1 plus the 2 in direction derivative in direction 2 of component 2 and plus the 3 u3. So this is the tangent of the fact, so in other words, this whole description here, if you want the description at the tangent space of an infinite dimensional kind of group of transformations. So the statement that divergence is 0 is really the tangent to the statement that volumes are not changed under this group of transformations, a group of volume-preserving diffeomorphisms, and this is the statement that at the tangent you are preserving volumes. So this problem needs boundary conditions, and we're going to not talk about that because that's complicated, so we're going to imagine this to be decaying, so the velocities we're going to flop to 0 at infinity, or we pretend things are periodic in this talk. And boundaries are extraordinarily important, and after all, they're integrated at the boundaries. And we have to supplement this with boundary conditions I mentioned. We have to supplement it with initial conditions, what happens at time equals 0, because I said time is non-negative. There is an arrow of time here, and the arrow of time goes one way, has to do with this little pesky coefficient viscosity, because we have, if you ignore the nonlinear terms, which are this guy and this guy, the u dot grad u and grad p, you have the parabolic equation, and that has an arrow of time. And that is a reflection of molecular mixing, molecular diffusivity. This term here, u dot grad u, together with the time derivative, it's called the material derivative. So this expresses actually time derivative along particle trajectories. You can imagine the flow moving, and if you, instead of sticking a point in space and letting the flow, observing the flow past that point, you can label the original position and move with the flow, and then the combination of these two things is the time derivative along that particle, so it's the acceleration on that particle. But viewed from a point in space, this thing looks nonlinear, okay? And it is nonlinear. So that's the equation, and the problem is to study this equation, its smoothness of the solutions of this equation for large initial data. And I have here an EG. So let me give you two kinds of examples, okay? For a moment, let's imagine that we are in Umbria, okay? There is a beautiful mustard field, okay, in the spring, okay? A few poppy seeds here so that you can see some nice colors. We are on a highway, but the highway is empty. We are allowed to green here, okay? The highway is empty, and then there is a fast-moving car. And again, we were allowed to green. Say, let's say it's a Lamborghini. And it moves like 200 kilometers an hour. And there is nothing else, okay? This creates a flow because I moved something and there is a resistance in the air and things become kind of like agitated. And these are essentially the realistic boundary conditions that we're not talking about. But you can imagine them also as an impulsive initial condition. So you have a velocity, if you are, let's say, within 10 meters from the ground, you have a velocity of about 200 kilometers an hour at time 0. The thing passed, and then things will settle down. Okay? So that's really a large initial data. Not a large initial data might be this. So you have a large vortex, and this is in Kansas, I think, where Toto and Dorothy are still in Kansas, I think, at this moment. And you're seeing a incipient tornado. Now, of course, the Navier Stokes equations, the way I described them, they ignore a lot of details. And this is really not a complete description because there is moisture, there is a lot of other stuff going on. Okay? So at this point, you might think that this is going to be a very cute talk with lots of pictures. And those who know me know better. So I apologize, it's not going to be a cute talk. So this is the end of the pictures. So I'm going to motivate a little bit the issues with some elements that come from turbulence. Turbulence is a very important endeavor. It has practical applications. It has attempts to theory. It is one of the hardest nonlinear problems, and it is hard because it is at human level. So many of the problems that have essentially a balance of scales and that have to do with intermediate scales where we live, they're very nonlinear and very difficult. So I will mention a few things about turbulence, and in particular I will mention a little more mathematical things about anomalous dissipation, and then I will describe elementary properties of the Navier Stokes equations and the Euler equations as we know them. And as I said, for those patients interested in something relatively new and who know the equations, I will show some computations and some formulas for the pressure. The pressure is a very important thing in this turbulence field and in Navier Stokes. And then I will end with a few words about outlook, in which I'm going to move away a little bit from the Navier Stokes equations and a couple of maybe open directions. So, turbulence. I'm quoting from a book by Uriel Frisch, who's a friend and a good theorist who spent his entire life working in turbulence. And the book is called Turbulence and the Legacy of Kolmogorov, and it is a wonderful book. So these are supposed to be experimental laws. So the first one you can read essentially says that if everything is kept the same, except for viscosity, which is lowered as much as possible, it's a theoretician. Okay, so I'll explain that comment in a second. The energy dissipation with mass behaves in a way consistent with, is a prudent math, with a finite positive limit. So I said it's a theoretician because you don't lower the viscosity very easily, because the viscosity is a material property of the object, but you can change other parameters, and you'll see the Reynolds number in a second, so that you effectively lower the viscosity. Numerically, you can lower the viscosity. So here is the energy dissipation per unit mass. So the dissipation word means that I take minus. Okay, so if the rate of change of the energy is negative and this becomes a positive quantity, this is a Kolmogorov notation. Epsilon is not necessarily small. And the statement is that epsilon is positive. Now, the energy is measured in an average sense. So you have here, let's say, for now, a Q, which is the unit box in which the things are periodic. So unit period box. Pretty soon it will be R3. So you take the size of the box, or the volume is that cube, and 1/2 because it's kinetic energy. This is the average kinetic energy. And from the Navier Stokes equation, exercise number 1, if you are allowed to do everything that you would like to do, integrate by parts and so forth, you get that this is equal to the average gradient squared divided by L and so forth times this plus C viscosity. So now let's read this again. finite positive limit, nu goes to 0, well, I have a product of two numbers. Limit is positive, 1 goes to 0. So maybe something becomes big here, and this gradient in velocity might have to become big. Okay? In one way or another. The second law is called the two-thirds law. This is the following. It, again, gives crudely. I will explain the Reynolds number in a second. At higher Reynolds numbers, if you take the velocity increment, I'm sorry, he wrote, and I wrote it with his notation v, it's our u. Okay? So that means I take u here minus u there, and the distance between here and there is L. Actually, you project on the direction of L, but that's not very important in this vague description. And if they are separated by a distance L, then the expected behavior is two-thirds power. So I explain here what the Reynolds number is. The product of a typical velocity, well, typical velocity maybe is the mean square velocity. A typical length, in the case of the Lamborghini, it was like 10 meters. In the case of that tornado, was a couple of 100 yards. And viscosity, okay? The Reynolds number is the most important parameter, one of the, maybe two important parameters in turbulence, and if Reynolds number didn't exist, we couldn't do experiments with wind tunnels. So the Reynolds number allows you to actually, it reflects the scaling properties of the equation, it allows you to actually scale down things, make an experiment at a certain scale, and infer things about larger scales. So it is, Reynolds number characterizes the regime in which you are. So the statement that this goes like L3/2 is essentially in turbulence, and this epsilon is the same epsilon from here. So in turbulence, the statement is that in multi-dimensional analysis, if you think about epsilon being a rate of change of energy, that's L squared over T squared by another T, L squared over T cubed, and then you multiply by another L, it becomes L cubed over T cubed, and you want it to be a U L over T squared, so there's only two-thirds power that can do that. Okay? This is supposed to happen in the inertial range, which means not really to L to 0, but for L larger than some cutoff. And the consequence, or equivalent way, is the famous Kolmogorov spectrum, which is kind of a Fourier transform of this, in one dimension and correlations, but never mind, that says that the energy decays like wave number to minus 5/3, and that's the same thing as this 2/3 here, and again, epsilon comes, and all is done by dimensional analysis if you wish, insisting that there is only one dimensional parameter, and that is epsilon. The only object that has dimensions is epsilon, and then if you're talking about wave numbers, they have dimension of 1 over length, and then things come up. So the Kolmogorov spectrum also has a cutoff, as supposed to decay like this up to Kd, and Kd is the cutoff where viscosity enters. And at that cutoff, you see, again, epsilon, but you see now that if viscosity becomes very small, this Kd goes to infinity, or L, this L goes to 0. So in some sense, you are taking this law to asymptotically become valid for all L, or this law to asymptotically become valid for all K. So there is a cutoff, viscous cutoff at the end, finally, and then things become analytic, smooth, and so forth. So that's, those are, let's say, experimentally verified to a very large degree. So the quality of the experiments, turbulence people like to fight, and they complain to each other about various details and so forth. By comparison to other experimental areas of physics, the quality of the agreement in the power laws is outstanding. So they fight about minor details. But, so if you look at power spectra and or ranges for instance, for the Nusselt number versus Rayleigh number, there are like 13 orders of magnitude of agreement. So it behooves us to explain this, okay? So here are some questions. Is the implicit, in this case, nu goes to 0, is the implicit of this product 0? Or not? Not 0, I write it in a different way. Is there a viscosity-independent, positive, I mean, energy transfer rate in the inertial range? So inertial range is this range of wave numbers, and you can think of the energy, you can Fourier transform the thing and truncate at k and ask yourself, is there a transfer from k to higher k's that doesn't change with k? In which case I will have non-dissipative, I will have dissipation of energy non-zero. The big problem is the velocity Navier Stokes solution smooth. Is the zero viscosity limit of the velocity further continuous with exponent 1/3? That's this 2/3 law that Frisch was mentioning as being a law. Is the implicit limit of the equations the 3D Euler equation, or an energy dissipative version of the 3D Euler equations? So these are ambiguous questions, and I mean by that, especially to my friends, there are versions and caveats, and you have function spaces, and certain things are not really, you can get both answers if you ask it this vaguely. But they are fruitful questions. So, and now maybe there are some engineers and real physicists in the audience. I'm going to be a little bold here. I think the analysis generates ideas that are relevant. And they're relevant to complex fluids with industrial and biological applications. If anything at all, at the minimum, they'll give you better ways to compute. To weather and climate, to fluid structure interaction, by which mean actually having fluids interacting with flexible boundaries, which have engineering and biological applications. To astrophysics, MHD, that's magnetohydrodynamics, plasma physics, and energy. So they are actually making progress in analysis, in pure analysis, is going to impact directly important applications. So there. Okay. Let's talk a little bit about anomalous dissipation of energy. So there are two ways to pass through these limits. First of all, we can fix time, a chunk of time of our choice, and then let this viscosity go to 0 and ask ourselves the question of dissipation of energy. If you formally take nu to 0, you get an equation without that Laplacian, okay, because nu is 0, it multiplies the Laplacian, that is gone. That is called the Euler equation. It's older than the Navier Stokes equation. It actually is due to Euler, and it's we'll talk about it pretty soon. So there is a conjecture by Onsager. Now, Onsager conjecture is a few years older than Kolmogorov's spectrum, Kolmogorov's Obovo spectrum, but they didn't know. He didn't know about it. And the conjecture is, in some sense, related to that. So the conjecture says that if you take Euler equation, no Laplacian, no viscosity, the solutions will conserve energy if the solutions are smoother than C13. That means a third of a derivative. For analysts, we know how to take fractional derivatives. One way of thinking about it is you already took one when you saw the 2/3 law of in the description of Frisch. You take differences and you ask differences around a scale L to scale like L to 1/3. So if they're smoother than 1/3, then solutions conserve energy, and the conjecture keeps going and says for less than 1/3 smooth solutions, there will exist CS solutions for which energy is dissipated. So the first part has been proved to a large degree, in the sense that if you go, this is a funny space, it's a world record space, but this has been done in stages by Gregory A., by Weinan, Titi, and myself, Duchamp, Robert, and then a bunch of friends more later. This is a complicated space, but let me say, L3, we're going to encounter this, and I don't. These are LP spaces, so you take the object and raise it to the third power and integrate in time. And the object is the norm of the function in this crazy space. The 1/3 is this 1/3, so it's a third derivative, and then there are some trimmings that, if you don't know what they are, forget about them. But they say, if you are a little better than 1/3, very, very, very little better, that's what all these trimmings mean, then the energy is constant. And this is the easy part, really. The hard part is to find solutions that do not conserve energy, and those first examples were given by Vladimir Scheffer. Then Schneermann produced solutions in L2 that dissipate energy. Scheffer proved that you can start from nothing, have something, and then nothing again. So it's a total non-uniqueness of the solution. And more recently, the last, let's say, 5-6 years, there is a very great improvement of the situation. So there is work by Delevis and Seikaidi, who went to CS spaces by using convex integration ideas, H-principle, and diminishing of nonlinear fluxes. So these are H-principles. So in other words, ideas that go, conjunctions of ideas that go back to Nash and Gromov, and the school, Schwerak, and school of people who do convex integration. So the current world record is 1/5, a little worse than 1/5, and this is due to Phil Isaac, who's graduating from Princeton and moving to MIT, and his additional idea was this material derivative, I mentioned time derivative along particle trajectories, is better behaved than the time derivative, and that improved things. Delevis and Seikaidi were about 1/10, and then the situation is 1/5. There is a long way to go between 1/5 and 1/3. Very long, because the new ideas are needed. Okay, so that was if you fix time, and therefore you take viscosity to 0, and if there are no boundaries, periodic boundary conditions, let's say, then you end up with solving Euler equations, no Laplacian, and then that's what's going on. The other order is to take time to infinity first. That's appropriate for experimental situations in, let's say, finite regions. So you can imagine, and some of you may have actually participated in these things, the Taylor-Kuet experiment, in which there are concentric cylinders, one is rotated, that's how you impart motion to the fluid. That's like the Lamborghini, except that it's a whole fleet of Lamborghinis and they never stop. So it's a shear-induced motion, and then you swirl that thing. The motion, if you look, they have nice plexiglass walls. You look at the fluid, you see a sea of bubbles that doesn't move anymore, and that is a permanent regime, long time behavior. Or you can look at a Rayleigh-Taylor convection, in which you heat from below a pot, cool it from the top. There is a lot of motion, heat, supply heat constantly. After a while, you reach what's called the permanent regime. And that is why you are in a certain regime in which the Navier Stokes are forced with a fixed force, fixed viscosity, and you wait till things stabilize in order, but do what they do. And only then increase the speed of rotation, get the Lamborghinis to go faster, heat a little stronger, and see the limit of nu goes to 0. So this is described by selected stationary statistical solutions, by which I mean you take the solution, I forgot to put initial data, maybe I didn't because it shouldn't depend on initial data. You take the solution of the Navier Stokes at fixed nu, you take a long time average, you maybe measure it with some functional, Then you record that, take very long time averages, and only then take the limit to 0. You get a measure, phi goes to some number. And this will end up by being an implicit statistical solution. Now, that's not the same as taking the initial value problem for short time. There are many more initial value problem solutions. This might select certain solutions. Okay? The hope is. Okay? So then anomalous dissipation, for instance, of energy would be that in some average sense, the quantity that's supposed to stay positive after a long time average stays positive. All right? In fact, that is, again, the non-vanishing of flux of energy. So we need to make sure that we understand that we're talking about transfer of energy to high frequencies and not just this quantity, because there are situations in which you can make this quantity go to infinity. There is no transfer of energy. So bounds for epsilon is an open problem. So now I'm going to come back and remind everybody some of the basic facts about Navier Stokes, very basic. So there exist global weak solutions with finite energy of 3D Navier Stokes equations. This is a result of Jean Leray around 1934. So global means global in time and also arbitrary initial data in L2, square integral. Weak means the solutions satisfy the equations, let's say as distributions, okay? After you test them with something, integrate that out. So they are not classical solutions. In existence, uniqueness, and regularization, or in other words, smoothness, of global solutions is done in 2 dimensions. And this is a long story. I cannot actually, and I apologize to all my friends, I'm going to refer to all kinds of results. I cannot quote everybody. I'm hoping that I'll be forgiven. The same thing is true in 2 dimensions for Euler equations, no Laplacian, which is a, let's say, harder problem. Smooth solutions, they exist, and I made the phrasing a little different here because here, if you start non-smooth, you become smooth instantaneously, and that's why I say uniqueness and regularity. Here, you start smooth and then stay smooth. If you have small data, small Reynolds number, in an appropriate set, then the 3D problem is exists global smooth solutions. For Euler, 3D Euler, there exist solutions only for short time. Smooth solutions for short. And a basic balance, this is the energy balance. If there are no forces that stir the fluid, the energy at time t is less than the energy at time 0. There is no increase in energy. And the rate of dissipation is proportional, as we saw, with the gradient in L2. So what are the blow-up problems more precisely? Let's say, let me put them both down. So you fixed initial data. Let's say that you are periodic or you are C0 infinity or decay, then your contact is supported and infinitely smooth. Initial data, let's say, in order to make them divergence-free, pretend that they're curl of some smooth vector. And then the question is, does the solution of 3D Euler, here is 3D Euler without the Laplacian, with that initial data exist for all time and remain smooth for all time? Then there's a play problem. Or does the solution of 3D Navier Stokes equation, the same initial data, here is the Laplacian, exist for all time and remain? So for Navier Stokes, we have parameters. So if mu is given, then you ask the question for all you know. Okay, smooth enough, C0 infinity, but all. Now, the 2 problems are related and different. Now, I'm going to start talking about how to graph these problems, and I'll start with some things that make them related, a way to graph them in a way that looks they're related, and then I'll mention some differences. So at this point, if you are on treadmill, the angle becomes a little 1 degree. We're going to go up a little bit in angle. So, related. First of all, there is an old result of Kato that for short time Euler solutions are smooth, and there is an old result of mine that for a long time, if you fix initial data and the time, and if you know that the Euler is smooth up to that time, then for the same initial data, Navier Stokes is smooth, provided the viscosity is small enough. And how small depends on time and on the entire Euler solution. So in particular, there is a gap between small viscosity and large viscosity. For small enough viscosity, depending on all these parameters, we know regularity. For large enough viscosity, we know regularity for all initial data. So that means small Reynolds number. And there is this gap, which I think is quite artificial and needs to be filled. Because that would be a weird situation in which you have, but maybe not, because there is not initial data per initial data accounting here. There is a deeper relation, because I'm talking about relation, and the deeper relation has to do with vortex dynamics, depletion of nonlinearity, and vortex reconnection. So I'll mention a few of that. So the vorticity is the curl of the velocity, so that's the antisymmetric part of the gradient. And it has an equation. You take the gradient of it, differentiate the Navier Stokes equations. The pressure disappears. You have a piece here. Here is the material derivative. In other words, there is transport here of the vorticity. Here is the Laplacian. And there is this term here, which is a very natural geometric term. It's not just an addition to the right-hand side, as many people in engineering and math think. It is actually a very natural term that gives you some conservation of circulation. But it is absent in 2D, and that's why 2D, everything is fine. And it's present in 3D. So there is no blow up in 2D because this guy is not there. And in 3D, this is really essentially the problem, and this problem is with or without viscosity. So, and also physically the vortices are the issue. So, vorticity is all. I'm going to give you we're going to try to grab this problem 3 times. And each time I'm going to say this is all. Because it is all if there are criteria. So, for the Navier Stokes equations, if you knew that the L2 norm meaning integral of the square of the thing, to the 4th power, so integral of the square of the thing to 1/2, so that you make it linear on the thing. So homogeneity 4. To the 4th power in time, if that would be finite, and by finite I mean finite. I don't know how finite. It doesn't have to be smaller than something. Just finite. Then the solution and every angle of the solution is smooth. What is known? Oh, sorry. The order in which I do this are the conditions. So for Euler is the famous Biel-Kato-Maeda theorem that says, from the 70s, that says this is essentially due to Leray. I mean, I cannot give a reference. It's essentially is the easiest to show a criterion, and everything can be traced back to this. So Biel-Kato-Maeda for Euler, it's a different quantity, different homogeneity. It's a stronger assumption in some sense. And if this integral, the integral in time of maximum, which is L infinity maximum vorticity, if that is finite, then the solution is infinite. What's known? For Euler, nothing. For Navier Stokes, again, this goes back to Leray. The integral of gradient u square and the integral of omega L2 square are the same thing. So this is a dissipation of energy. Okay? What is the story about geometric depletion of nonlinearity? Let me go back a little bit and remind you of this term. The reason why this term is absent in 2D is geometric. Omega points up, and the velocity depends on variables on the ground. So the scalar product is 0 because of geometric. Omega is a vector that's parallel always to the same direction, the direction perpendicular to the plane of motion. So 2-dimensional motions are motions in a plane, and there is a perpendicular vector. So that in particular direction of vorticity is constant. So Charlie Pfefferman and I, 20 years ago, had a theorem that says, generalized in some sense the two-dimensional situation, and looked at the directions field of vorticity. So the vorticity normalized and creates a unit vector, and if this is smooth in regions of high vorticity, so it doesn't have to be smooth where the vorticity is zero, it might have trouble being defined there, then the Navier Stokes solution is easy. And this has been improved over the years by a number of threads, removing the smoothness here. So we asked for Lipschitz, and it's further is enough, and so forth. And recently by Rich, who did actually a very interesting combination of coherent patterns and the criticality of the equation. I cannot get into that. And at our workshop here, I learned about the work of Professor Giga and his collaborator, and I haven't seen the preprint, so I hope I'm having the right collaborators, where he studied this problem with boundaries. And that's a big change and difficult improvement, but essentially the conclusion is the same. So you have vortex reconnection is a regularizing mechanism. So this is like this. What happens, let's tell you the story. There is a story. So strong coherent vortices form. So what that means is if you look at the field of vorticity and you paint in only the regions where the vorticity is more than 90% of its integral of the maximum, right? So more 90%, let's say, than the L1 norm, okay? Okay, the L1 norm in Navier Stokes actually is not increasing, so it's a very good way of quantifying this. So we look at that, and then people have actually numerics, and then what do they see is tubes, intense tubes of vortices, and as they stretch, because of circulation, as you know from watching skating maybe, there is a conservation of circulation. The shorter the closed path of velocity does, the faster it has to move. They stretch, they become coherent and straight, intense, narrow vortices, and they approach. And when they approach, they violate the smoothness assumptions because they would have the gradient in space of the direction go to infinity there if they would cross. But they encounter the viscosity, and there is a bound, a weak bound, that relates the viscosity, the magnitude of the vorticity, and this gradient of psi. And it says this integral space-time is less than the budget of energy that you had originally. So this says the viscosity wants this guy to be finite. When they approach, they reconnect. By reconnection, we mean that one arm goes with another arm. Essentially, they do one of these chromosoidal things. Move apart, and then they decay. Okay? The reconnection is a topological change. It's not allowed in the Euler equations, but it's perfectly allowed and happens a lot in viscous fluids. And this happens several times, and if you don't force it, the thing goes down. So this is a scenario. It's not a theorem. Okay? The theorems are an L infinity bound on gradient, or maybe Hilbert on the gradient, implies regularity, and this pathetic little bound on the gradient. Okay? So there's a gap. But I think there is physics behind it. So another way, you'll see at the end, I'm going to mention some stochastic things. Majority of events will be this event. Now I'm going to talk about why actually the two problems are different. And in Navier Stokes, there is a famous condition. So why they are different? Navier Stokes is a blow-up for the momentum. It's a blow-up of a velocity. Velocity has to go infinite. Euler is a blow-up of gradient. So that's the difference. So you'll see here, in Navier Stokes, there are famous old conditions, and I give only one of them, due to Prodi, Serin, Ladezhenskaya, Poyash, people mention lots of names, Prodi and Serin. So that say that if the maximum velocity is squared is time integrable, then everything is fine. And This is for Navier Stokes. And what's known, which I call FGT, Foyage Diopétement, and Tartar, I'll mention in a second, what's known is that the time integral of u in an infinity is bounded. This is a very nice bound, actually. It tells you that bounded by the energy budget, by whatever energy you had initially. So this tells you that you cannot carry any blow-up that occurs. If you think it happens here, it will happen at most at a distance, this is a distance, at a distance that's prescribed a priori, cannot go far. So you cannot miss catching it. But there is a gap. Okay. There is no such thing for Euler. So there is another class. So these are all classes of functions. L infinity means bounded. L3 means the third power absolute value is integrable. So there is another very important, and in this talk will become more and more important if the talk can go on a little longer, L3 bound. So there is the Foyage, the Prodi-Serrin conditions go for other LPs than L infinity, but they stop at L3 for a reason, and that is that this is actually a much harder theorem, and it was proved essentially by contradiction. Not very long ago by Escauriaza, Seregin, and Schwerak, and that says that if the maximum of the L3 norm is bounded, then things are okay. And for L3, what's known easily by some interpolation and stuff is that the L3 norm is not bounded, but rather integrable to the fourth power. So there are always these tantalizing differences. It's not like the thing is completely hopeless. There is a finite distance, you think, especially if you're not an expert. There is no such thing for Euler, and no such thing for a very good reason. Euler is not really controlled by the velocity. So the Navier Stokes problem is really very different because of that. You need to create infinite momentum in the problem, infinite velocities, and you might think at first, well, the Lamborghini went to maybe 250 kilometers an hour, and then things started to settle down after that. So where is that infinite velocity coming from when everything settles down? So, yeah, we agree. So that's a physically hard to imagine. On the other hand, there are other experimental data in which you can very easily see that infinite velocity, and you do that every morning in your, when you turn on the faucet and the drop falls out. Actually, the pinch-off ends up by having infinite velocity for a very, 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 very short time. So, Berger's equation, which is an equation that doesn't have the incompressibility and doesn't have the pressure, does not blow up if it has a viscosity, and does blow up if it hasn't. So here is the Berger's equation in 3 dimensions, and here it is. There is no pressure, there is no divergence free. If you erase this Laplacian, you shock. You create discontinuous velocities, infinite gradients. If you restore the Laplacian, the solution is smooth, and that is because there is a maximum principle. It doesn't increase the velocity. So for Navier Stokes, the straightforward maximum principle that I was just mentioning is obstructed by the pressure. I struggled to find the right words. I'm not saying that there is no maximum principle in Navier Stokes. It's simply we don't know how to find it, maybe, we don't know the right quantities. But there is, the Lamborghini past. We would like to say things go down. But we don't know how to find it. And the usual one, which says the maximum of velocity goes down, well, you try it and you see the pressure. And the pressure is a non-local object. So the pressure, you'll see formulas for the pressure. The pressure doesn't depend on the point where you're sitting, and because of that, there's a problem. So there are sufficient conditions based on the pressure, Navier Stokes. And I'm going to quote one, very easy to prove, actually, maybe I'll even show where it comes from, by Berselli and Galdi in 2002, that says if you take the time integral of the L3 norm of the pressure, again, this test P3, you take this squared, and if you knew that that's integrable in time, then U is smooth. And Segovin and Schwerak, they showed that actually you need only lower bounds. You don't need the absolute value of P. And that's a very interesting and harder theorem. This upper bound things are very easy. So here is why they come. You can write down an equation for LQ evolution of the velocity. They come from the Prodi-Serrin conditions. You have the conditions of integrals of velocity to some power. You take the time derivative of that. Everybody else is either dead or benign, and only the pressure survives. You integrate by parts the gradient of the pressure, hide the gradients on velocity on the gradients that are given by the viscosity, end up with this inequality. Q is the power that you raised u to, and if you're larger than 2, you recover very nicely that if Q is equal to 2, you don't have any growth, and you pay a 1 over nix. So obviously, if you put Q equals 3, you would integrate this, get a finite quantity, you get L3 to be bounded, and you apply the Escariaza-Seryogin-Shvera result. That's basically how this, which was around the same time, goes a little earlier. Okay, so now for those who are patient and are still with me, I'm going to write down some formulas for the basic. Now, the treadmill ramp moves up a few notches, and the degree of boredom will increase dramatically because I'm going to write formulas. Okay? So those who are interested in these will be interested. I believe that they're very interesting and very important. So we start with taking, this is the equation that the pressure satisfies both Euler and Navier Stokes. It is the statement that the divergence of the momentum equation is 0. In Navier Stokes, that momentum equation had a Laplacian of a function with divergence 0, and there were no boundary conditions. So when you take the divergence of the Laplacian, it goes inside the Laplacian, it vanishes. So this is the equation. And we don't have good boundary conditions for the pressure, except in periodic case when you say it's periodic, or at infinity you might insist it's the case. So these are the equations, and we're going to try to express P in terms of U, locally. Okay, so that's the news. That's usually it's a very non-local thing. You can invert this and get 1 over 4 pi integral x minus y right-hand side y. Okay, that's the fundamental solution of the Laplacian. But that requires you to know your velocity everywhere. Okay, we don't want that. So U is given divergence free at this point, doesn't need to be a solution, but of course we are thinking about solutions. And we're going to take spherical averages. This is this will be on your test. Okay, it is on your test in maybe second year. Okay, so you take spherical averages. It's essentially level of Fries-John's book on VD. Take spherical averages of, and denote them by bar, at distance r. So this is the ball of radius r around my point x. And I take a spherical average. The only little trick I'm going to do, which is pure luck, I think, is that I'm not going to talk about the pressure. I'm going to take the pressure average, and add a thing to it. And it turns out, by luck, that this thing is what is needed. And this is actually what it is. It is the average at the same distance r of the velocity dotted into the direction. So if I'm here, I'm taking r direction, I have a radius, the velocity is a vector. I project that velocity on that radial direction. It's called the longitudinal component of the velocity, and that is squared and averaged on the sphere. So I call that B for bounded. This object will be bounded. So there is, once you do this, there is a monotonicity lemma. Those of you who know elliptic equations, monotonicity lemmas are an important thing. And in this particular case, I put quotation, but really not monotonic. But you have a local, ODEs, if you wish. And this is on the web now and on my webpage. So you take a point, you take a place, and you take any solution, including the harmonic pieces that are there. I take any vector, and I compute the R derivative of this average pressure plus something, and I get an equation. And the equation has a nice symbol. This is simply the unit vector monomial. This is the Kronecker delta, and this is the displacement between u and an arbitrary vector v. So let me stop. So this is tells you that the R derivative of the average pressure is proportional to velocity increment integrated against harmless state. Okay? So here is, sorry, looks horrible, the representation formula. With this representation formula, number one, it tells you that P minus P bar is averages of squares of increment. And all the knowledge is in a ball of radius r, and r is arbitrary. And I don't need to know anything outside. So, in order to digest this for a second, think in terms of orders of magnitude. So it tells you that P minus P bar is of the order delta r u squared, where delta r, let's say, is the supremum, distance r, I think the modulus of the distance between the vector u at distance r and the vector u where I'm interested, square that, call that delta r of u, and I have here that P minus P bar is of the order delta r of u, and this is an average, the r rho over rho of the same thing. So the fact that P is arbitrary is reflected here because P is known up to an harmonic function. But for an harmonic function, P minus P bar is 0. So this is determined by information of the pressure totally, the information about the velocity totally and locally, modulo P bar. Now, I said that P bar is bounded, I lied, but it will be bounded in a second. So I take a wave function that looks like a ramp, 1 up to 1, and then goes down to 0, and then continues to 0. So it's a wave function. And then I represent the pressure as now something really bounded, beta, and the rest, which is an oscillation. And beta is, again, one more average of P bar. P bar was a spherical average. Now this becomes an annular average. It's an average on the annulus of the pressure. And now this is going to be, you'll see in a second, is going to be bounded. So pi is simply the average of that thing before. You don't need to remember anything, of course, but essentially here is the annulus. You have the annulus, you have increment of the velocity with respect to the center square. That's all you need to remember. You have a singular integral with a very nice symbol, and very classical singular integral. So we have some bounds. Okay, so let's see. When am I supposed to end?
A couple more minutes.
Okay. So let's go a little fast to the bound. As I promised, this is bounded in two ways. I have, if I have only energy information, remember that's conserved both Euler and Navier Stokes, or bounded both Euler and Navier Stokes, I pay a price of r minus 3. If I have H1 information, which is also integral in time in Navier Stokes, I pay r minus 1. And these come easily. And now, if I take the representation that assumes decay at infinity, only now I'm doing that, which means that the pressure is an expression in terms of Riesz transforms and U, then I get uniform bounds just from pressure bounds, uniform bounds that are known essentially for the pressure that do not depend on R. And then I can interpolate between this and the L infinity, and I get any kind of decay at a price that interpolates between these. Okay, and then also I can get for the gradients a bound that is in terms of L3 and gradient Q. Remember, I care about L3 more than other spaces, so this will give me a bound for gradient. How about the other guy? The other guy is small. So the other guy is small if the velocity is Dini continuous in a very simple way. So this increment needs to vanish with z at any decent rate. Any decent rate. So I'm having a singular integral here. And this is the first bound, and consequent are that pi is like r squared times the gradient in any norm. Okay? And in particular for L3, which I like, this goes like r squared times Laplacian, but the Laplacian actually, we have also these bounds that are known for all the pressures that are independent of r. So first the operative in whole space tells me that the Laplacian is integrable in weak solutions of Navier Stokes on small power. So that means that pi in L3 is less than a constant times r squared. And that constant is almost everywhere finite in time, but only because 1/3 power of that is integrable in time. So there are singular times, and because of that, I cannot say that this is less than 1. But if I knew something, so these are not criteria for non-blow-up in terms of pi. So the main idea is the following. Beta obeys bounds which guarantee global regularity at any r. So if I could ignore pi, I'd be done. And the other thing is pi is small for small r. So Lamborghini passed, and we're done. However, we have to actually do the job. So here is one possible thing. Imagine that not only that I take r, I'll take it as a function of time. Let's pretend that the thing blows up at capital T, and I'll take it as a function of time that goes to 0 at capital T, but it will have to go to 0 not too fast. And then when I look inside pi, I require only to look at regions where the velocity is larger than some huge velocity, for example, the Lamborghini. And so I look there and I discover this L3 square is fine. Then U is fine. U and all the cousins are fine. Or if there exists a U like before and the same kind of R, and I have a bound pointwise at R of t that diminishes in time, a bound in terms of beta, so actually I'm saying pi is less than beta, or maybe pi is less than beta plus U squared, or maybe pi is less than beta U squared, and another function that's in L2 of L3. Okay? Whenever U is large, then U is infinity. So, in particular, if this Dini condition in L6 is valid on the region where velocity is large, you have LET. So those are essentially translating into elementary, really, consequences of the formula and the common sense that in principle pi should not be there too much. All right, so I would like to, I have a couple more slides about outlook, if you don't mind. I'm going to skip this. Okay, so this deserves a little discussion, so I'm not going to. So there are other models. So there is absence of anomalous dissipation in a model called SQG, and that's work with Vlad Nikol. There is presence of anomalous dissipation in some dyadic models. That's work by Cheskilov and collaborators. So there are models in which you can construct this non-vanishing flux. There are other models also. Breakdown for smoothness for large data in waterways is a recent work of a Spanish. I'll make Charlie honorary Spanish, so then it's a Spanish group. And the and Sporer was here. There is global regularity for small data in waterways, which is a very non-trivial problem. And these are recent results in two dimensions, which is harder. I'm going to quote two large data weak solutions that are really very special. One is old by former student Resnick, which is really very non-trivial, and an amazing result for Tini is a model for complex fluids by Nader Masboudi. We wish we had this weak solutions in more equations for complex fluids, but we don't know at this point. And large data results, so the kind that we would like here for dissipative, critical dissipative SQG, the results by Caffarelli and Vasseur, recent-ish, 2008-7, Kiselev, Nazarov, and Volberg, and we have much more later the result with Vlad Nikol that I think gives the proof from the book, I'm allowed to say so, based on a nonlinear maximum principle. There are results that take advantage of special structure for the pressure and prove global regularity for the so-called primitive equations of ocean air circulation, and these are results of Tsao and Titi a few years ago, not long ago. There is a result, it's an easy result with my student legal on order beats another complex model that is open, kind of like Navier Stokes, they do it. And very recently, two amazing results about long-time behavior, one by Bedrosian and Masudi, kind of a quote-unquote Landau damping, because people heard about Landau damping, but this is stability of Couette linear shear, reading on Libya. And the very recent, our workshop result about super exponential growth of gradients in 2D Euler by Kiselev and Schwerer. So these are amazing results. And then there is numerical evidence right in our workshop by Tom Howe and Luo about axisymmetric 3D Euler blow-up due to boundary effects. So something that we didn't talk at all today. So here are, this is my last slide. I have 3 bullets here. Boundary effects, it's not only because of this recent work of Tom Howe and Luo. Vorticity is generated at a boundary. All turbulence is generated at a boundary. I didn't talk about the zero viscosity limiting the presence of boundary. That's an essential open problem, and that is not understood. This is a little hobby horse of mine, stability implies regularity. If you formulate it in some sense, L2 stability of weak solutions regularities. In other words, the things that you observe are the things that are observable. It's a tautology. But it has a little bit of beef, not a whole lot. And finally, a stochastic description. So there are stochastic descriptions, meaning that you can represent the deterministic Navier Stokes as an expected value of the stochastic process. But there are also issues with enlarging the whole description in which you allow for stochastic forces. And the purpose of this would be perhaps to understand the statement of what are the chances of actually have the Lamborghini pass and the velocity going to infinity while on average goes down. So can we actually, if not prove that for all possible cases, can we actually understand that this is really what's normally happening? And that would require a little bit of stochasticity. So with that, thank you very much for your attention, and sorry to
We've got a little time for a couple of reasonably quick questions.
Can I ask a fundamental question? Are you doing anything with category theory could really be using functional calculus, whereas you use functorial calculus, because you're at third order level, and you're way out of outside the axioms of functional calculus. And all those terms are really patches to cover those differences.
We come from a very modest background. We would like, and the way these things are, actually first year I didn't do that, but first year education remains the situation here is one in which we are dealing with a priori bounds. So the a priori bounds are done in the smooth category. They are done for solutions that are infinitely smooth and infinitely well behaved, and we would like to find out how well controlled they are. On the other hand, the weak solutions, they are done in another class of functions, much weaker, but not so different. And other people, I tend to try to prove things starting from smooth solutions and keep them smooth. Other people are looking at this larger class, okay, of solutions, which are these weak solutions, and try to discover new properties that would actually diminish their complexity and find out that they're actually less complex and more infinite. So I think that the frameworks are there. So a framework would not save the day.
One more question? Okay, thank you very much again. 5-minute break.